thank you for coming today. My name is ENorris. I'm the Regional Sales Manager for AON. And today we're going to talk about the efficiency design of DX package rooftop units. Later on in the question session, we're also going to have Matt Yielding with Texas Air Systems join us. He'll help me answer any questions you may have further in. We're going to start off with the agenda today. We're going to first talk about a few of the different systems that will be evaluated. From there, we're going to investigate what's required for an efficient system. We're going to look at some different fan types, some different compressor types, and then finally we're going to wrap up with what's required for precise space control. And we're going to look at both compressor and fan control strategies in order to minimize energy use and provide maximum occupant comfort. Starting with the system types, we're going to look at three types, and one of them is going to have two variants. First, we're going to look at the constant air volume system. That's going to be our baseline. That should be the highest energy use of all of them we're going to look at. But we're going to look at what happens if we just change the fan type from a forward curve fan to a backward inclined plenum fan. From there, we're going to look at two-step compressor and fan operation. That system will use a forward curved house fan. And then finally, we're going to look at single zone VAV, which is our single zone variable air volume system. It will have a variable capacity compressor and the backward inclined fan. So we're going to jump straight into some psychrometric properties and look at what happens at not only full load, but also part load on our systems. And we're going to start with the constant volume system. In this case, we've got a 18,000 BTU per hour sensible load and 3,250 BTU per hour latent load in the room. That does not include any of the ventilation requirements. That is only the room sensible and latent. You can see in this case we're at a DFW, or Dallas-Fort Worth, design cooling day of 101 dry bulb and 75 wet bulb. We're bringing in 200 CFM of outside air, and we're using a total of 31,000 BTU per hour. So we'd have to use a 3-ton unit in order to meet this load. Now everybody knows that when you have a 3-ton unit, everything runs at 400 CFM a ton, so we're going to run 1,200 CFM of supply air. But what we see almost immediately is with that unit running at 1,200 CFM of supply air, we've got a 61.4 degree leaving air temperature from the unit, and therefore our space condition, where we've got a set point of 75 degrees dry bulb, has a 58.8% relative humidity. That relative humidity is well outside, or just right at the edge of what ASHRAE recommends, which is the American Society of Heating, Refrigeration, and Air Conditioning Engineers. That's one of the main bodies that the HVAC industry looks at. And they recommend that you maintain between 40 and 60%. We're right on the edge at full load. But I wanted to look at a part load condition as well. So I looked at the same DFW chart from my ASHRAE book, but now instead of using the 101 degrees, I used 83 degrees dry bulb with 77.3 wet bulb, which is the design dehumidification day for the DFW area. Now I made some assumptions on this, and I decided that when you take out all the solar load and you drop the outside air temperature, so you lose a lot of your transmission loss through the walls on an exterior wall, it would drop the sensible load by about half. On your building, it may be something different, but this is what we're going to use for the rest of the day as we discuss the psychrometrics of this system. Now, when we drop the sensible load in half, we're in a constant volume system, so we still have 1,200 CFM. That means our dry bulb temperature leaving the unit has to be 68.2 degrees, and now our relative humidity is up to 74%. We have a problem. This is not going to be a comfortable room. It's going to feel stuffy, it's going to feel muggy, and nobody is really going to enjoy being there. So we need to find a better way to take care of this. Well, I mentioned before that we always use 400 CFM per ton on equipment, And there's no real good reason for just using 400 CFM per ton. So in this case, I decided what happens if we drop that to 300 CFM a ton, and we're going to run 900 CFM of supply air. Now our supply air temperature drops down to 56.8 degrees, all else being equal. Still have the same 18,000 BTU per hour sensible, 3,250 BTU per hour latent load, and we're at 51.3% relative humidity in the space. Everybody's going to be relatively happy in there. There'd be some that thinks it's too warm, some think it's too cool, but that's not unusual. On the average, people are going to think it's a relatively comfortable space. But we still have to look at what happens with that part load condition. So our constant volume system, now we have to increase the leaving air temperature of that unit to 65.9 degrees. And we're back up to 69.5% relative humidity. By dropping the airflow at full load on our constant volume system, now we have that same lower airflow, and we gained on it compared to what we had before, but we're still well outside what is recommended by ASHRAE and what's needed for occupant comfort and for protection of the building. As things get too humid, it can cause problems within the building as well. One of the other challenges we're going to have with that constant volume system is we're using on-off compressors. And this was a chart done by the Department of Energy, and the first time I saw this was about 15 years ago. And it looks at the evaporation effects of on-off compressors due to cycling. And right now we're showing the first 45 minutes of this test. And at time 0, the compressor is turned on. And we have the red part there, and that is our sensible cooling. That's changing the temperature of the air. We have the blue, which is our latent removal. That's what's taking the water vapor out of the air. That's what's dehumidifying. And it's running along and all is well with the world. Except we have another challenge. It's an on-off compressor. Once that set point is met, we're going to turn off the compressor, and it's going to re-evaporate that water back into the airstream. So we look at this over a 24-hour cycle. And in order to understand what we've got here, this is a 24-hour chart plot. And the green concentric circles you see on that plot that start at the inside and work their way out are 10 units. And that's either relative humidity or degrees Fahrenheit. And then we've got the relative humidity, and that's that green sawtooth line you see. In this case, we had on-off compressors, and relative humidity was controlled at 60% plus or minus 14, meaning it ranges from 46 to 74% relative humidity. This is not going to be the control we want. Our dry bulb temperature then ranged from, it was set at 70 degrees in this case, and it was plus or minus 3. So we ranged from 67 to 73. And it's a little over 100 times throughout the day that this turns on and off. This is not going to be a comfortable room. You're going to be cool, and then you're going to be warm, and it's going to be dry and then humid, and it's just all over the map, and nobody's ever going to be comfortable because it's completely inconsistent. If it was consistently uncomfortable, at least you could plan accordingly, but in this case, it's not even consistently uncomfortable. So now we want to look at some energy consumption. And I modeled a 4-ton classroom. This model was done on a little bit different classroom than the previous model, but it's going to work about the same. Again, this is the climate data for Dallas-Fort Worth area. The green part of the bars you see there, and each of those bars is a 5-degree temperature increment from 102 down to 22. And the green part is your unoccupied hours. The red part is your occupied hours. And everything we're modeling today is going to be a classroom. Now, that being said, if you've got another type of facility, be it a classroom, be it a patient room in a hospital, whatever type room it is, the same basic concept is still going to be there. The magnitude may change, the amount of difference may change, but the concept will still be very valid. So we look at our constant air volume supply fan comparison. In this case, we've got a forward curve fan. The fan efficiency on our forward curve fan is 46%. our backward incline, our plenum fan, is a 65% efficient fan. And the way I came up with those efficiencies is I picked a CFM and a static pressure, and I selected 2 fans. And I selected fans as an engineer. I tried to select the best fan selection that had the efficiency, the turn down, had the ability to move up and down a little bit when the external static pressure wasn't exactly what was calculated on the drawings. It had everything in there. Both of these systems use on-off compressors, and both of them have the condenser fan controlled with a fan cycle switch, meaning the condenser fan is going to come on with the compressors. And you can see there, just by changing the efficiency of the fan, we can change the amount of energy used in the system. And that's going to become a big deal later, because in any given year, the HVAC system, the #1 user of energy in that system is going to be your supply fan. And I know some of you are going to say, but I looked at the nameplate on the unit and the compressor has a higher amp draw than the supply fan by a lot. How could it possibly be less energy? And if the compressor is running, it will use more energy, but the difference is now we've got a supply fan that has to run anytime the building is occupied. During unoccupied periods, it will cycle, but the compressor only runs when there's a call for cooling or for dehumidification if you've got a reheat coil in there or something like that. So it just doesn't have as many run hours per year. So we need to solve our humidity problem. And the first way I want to look at to solve that problem is to add modulating hot gas reheat into this system. And we've got our same 18,000 BTU per hour sensible load, 3,250 BTU per hour latent load. Our supply air is 900 CFM, so we determined earlier that if we drop that supply air down, we'd get better humidity control out of the system. But in this case, now we have 2 methods of control. We can control the dry bulb temperature by adjusting the leaving air temperature from the unit, but we can also control the relative humidity because we added that reheat coil in there. That is, in this case, a modulating hot gas reheat coil. It uses the condenser side hot gas from the refrigerant to reheat the air after you cool and dehumidify it in the evaporator coil. So we're going to cool that air down to 54.2 degrees coming off the cooling coil and add 724 BTU per hour using our modulating gas reheat. And now we can provide 75 degrees and 50% relative humidity. Our unit gross capacity is 32,766 BTU per hour. And that's going to become important on the next slide when we go to our design dehumidification day. And while we're still able to very precisely control the temperature and relative humidity, we've got a supply air of 900, but now our leaving air temperature is 65.9 degrees. We've still got 54.2 degrees coming off the coil, and we're going to add 9,724 BTU per hour back in. And our unit gross capacity went from a little over 32,000 to 34,869 BTU per hour. That's because there's more energy in that design dehumidification day than there is the 101 degree dry bulb air in Dallas-Fort Worth. So it takes more energy to cool and dehumidify that air. So we can clearly control it, but it comes at an energy penalty in that we have to cool 900 CFM of air down to 54.2 if you've got a 3,250 BTU per hour latent load, independent of what's happening with the sensible temperature. We're just going to add more heat back in with that reheat coil. If you've got a space that requires a constant volume, you can't use VAV, and it requires very precise control, this is the method I would recommend using. It passes all energy codes because it uses the same cycle, but it's not necessarily the best way to do it for a basic comfort cooling type application. Your classrooms, your patient rooms in a hospital, conference rooms, anything along that line. But when we look at putting a variable capacity compressor with our modulating hot gas reheat on that same building we had before, now you can see those circles for the green circle for the relative humidity and the blue one for the dry bulb temperature are now much more consistent. It varies plus or minus 0.5% or plus or minus 5% on relative humidity and plus or minus 0.5 degree Fahrenheit on dry bulb temperature. So we've got a very consistent leaving air temperature. We've got a very consistent space condition. And that will aid with comfort of the occupants if it is consistent. So now we're going to look at our two-step compressor option. We're going to assume that the compressor has capacity steps of 167% of capacity, of its full load capacity. That's the most common with variable capacity compressors, or pardon me, two-step compressors, is 67 and 100. Some of them are going to be 60 and 100, but in the sizes that we're talking about today, we're going to go with the 67 and 100% for our two steps. We also are going to assume that we have a two-speed supply fan. It's going to be a forward curve fan, and on ventilation mode and also with first compressor stage, we're going to be at 67% of full load capacity. If we go to high capacity on the compressor, we're going to go to high speed on the fan and therefore go to full load speed. So let's see what happens to our psychrometrics. And we look at our full load day, and really nothing changes because we've got the same 900 CFM, the same 56.8 degree leaving air temperature from the unit. So we're still at 75 degrees and 51.3% relative humidity. So nothing real interesting happened there, but we wanted to remind of that condition. When we go back to the dehumidification condition, however, now instead of a 900 CFM of supply air, we've got 600 CFM of supply air, and our supply air temperature is going to drop to 61.4. Now, if you recall before when we did this at 900 CFM, we were at about 70% relative humidity, and we've been able now to get this down to 63.8% on our design dehumidification day. Another advantage we've got is we did decrease the horsepower of the system now, the brake horsepower, and we'll look at that a little bit more when we go into our single zone VAV system here in just a few minutes. But we are able to save some amount of fan energy doing that. So we're going to look back now at our two-step fan energy, and we've got the two-step fan and we've got our constant volume systems, both with the forward curve and the backward inclined fan shown now. And you can see that in just about every month, the two-step unit does use less fan energy compared to the constant volume system. If you compare it to the constant volume system with the forward curve fan, it's considerably lower in every month. But now we can add something else in that we really didn't look at with the constant volume system because the only thing that changed was the fan, therefore it's the only thing that would affect the total energy usage. So we're going to look at the total cooling energy, and this is the supply fan, the compressor, and the condenser fan only. We're not looking at any other parts of the system except the air movement for the cooling. And you can see that in every month we've got lower energy use on the two-step versus either of the constant volume systems, which is what we would expect as we decrease airflow at part load and we decrease compressor capacity at part load. We're going to get better efficiency on the system. But now I want to look at the single zone VAV system. And if you're familiar with a traditional VAV system, this will look somewhat familiar to you, except there's a couple changes. We've got a single zone system that will feed one zone from one unit. The supply airflow is going to change based on the space load. So that will work just like your VAV box would on a traditional system. As your space load decreases, you need less air in order to maintain your space temperature, and you close a VAV box, except we don't have any VAV boxes. So now we're going to slow the fan down. So we're going to put a VFD on the supply fan or an EC motor and adjust the fan speed based on that space condition. Your unit capacity then will change to maintain a supply air temperature. And so now our supply air temperature is a set point, not a output just based on whatever CFM we're at. We're going to control that with the compressor. So we're going to have some type of a variable capacity compressor in order to make that work. And like I said before, there's no VAV boxes required for this system now, so we don't have that control. So on our single zone VAV system, what's required for single zone VAV equipment and under what conditions is it beneficial? Well, first of all, we need a variable speed supply fan. We can either do that with an AC motor on a VFD, or use your brushless DC motors. It's a EC motor, your electronically commutated motor. And there's advantages and disadvantages both ways. That's a discussion for a different day, which has its merits in which case. We need a variable capacity compressor of some type, and we can use a digital scroll compressor, we can use a VFD-driven compressor. Either of those systems will work just fine for what we're talking about. And then finally, if you're going to control the fan speed and you're going to vary the compressor capacity, it's really important to control the speed of your condenser fans. If you try to use condenser fans with fan cycle switches, the way those switches work is they turn on when you hit a high pressure, they turn back off when you hit a low pressure, and it goes back and forth between them. And the way you test motors to failure is you turn them on and off a whole bunch of times, and the way you test coils to failure is you change the internal pressure from high to low and high to low a lot of times, so it just becomes a machine that will tear itself apart a little bit quicker. So you need to control the speed. Now you're going to have a pressure transducer on it, and you're going to control the condenser fan speed in order to maintain a much more constant condenser pressure. It'll also help with avoiding some noise complaints if it's sitting outside a window with occupants nearby, because it will be a consistent sound level, not that on and off that you're going to get using a fan cycle switch. Another advantage we have of single-zone VAV systems is we've got our full load capacity. In this case, it's 8,000 CFM. I know I've been dealing in different capacities throughout the day, but this is a graph that was already done, so I used it. And if we set it at 900 CFM and went to 58% of full load, what you're going to learn is all the math still works the same way. At 8,000 CFM in this case, the full load is 4.5 brake horsepower. We're going to reduce that load to 4,650. It's 58% of full load, and it will reduce the full load brake horsepower the brake horsepower needed from 4.5 down to 0.9, which is 20% of full load. So you get some really dramatic energy savings from the fan because of the way the fan laws work. The horsepower decreases with the cube of the differential of airflow. So if you drop your airflow in half, you've got 1/8 the brake horsepower required. So you get energy savings very quickly as you turn down fans. Another benefit is as you reduce the airflow, you can have a reduction in fan noise due to the change in speed. If we look at the generic fan I have shown here at 2,000 RPM, it's at about 90 dB. If you drop that in half to 1,000 RPM, you're at a little over 70 dB. So you've got a dramatic difference in sound power as well. Now, if we're talking about a classroom, you're not going to get complaints when it's 100 degrees outside because the equipment is loud unless you made a major mistake. When everybody complains that the equipment is too loud in a commercial building is almost always when you have a part load day. It's 75 degrees outside. And that teacher's in the classroom and thinking about the unit at their house, and when it's 75 degrees outside, that unit does nothing, therefore it makes no noise because there's no internal load to speak of inside that house. So it doesn't run very much, if at all. The teacher in that room does not understand internal loading of people and lighting and computers and all the other stuff we have to deal with. They don't understand ventilation requirements. They don't want to understand it. They don't need to understand it. We need to find a better way. So by decreasing the airflow, now that unit will be much quieter on those part load days because you're not going to be at full airflow at that time. So now we want to look at the psychrometrics of this system. And we look at our VAV system psychrometrics, and we got a 56.8 degree leaving air temperature from the unit. We've got 900 CFM. Nothing's changed. And I told you we're going to look at the brake horsepower a little bit. In this case, our supply fan is at 2.5 inches of total static pressure, and it's working against 0.64 brake horsepower at our full load. But I want to look at what happens on our design dehumidification day, and I put in a set point of 55 degrees for our supply air. We've still got our 9,000 BTU per hour sensible, 3,250 BTU per hour latent, and we're going to provide 55 degree air into the space to maintain 75, and you look and you see that we're at 54.7% relative humidity. By going to this method, now we've got a room that can be controlled fairly well on temperature and humidity. And that's going to help with occupant comfort. It's going to help with a lot of other issues inside that space. Now you remember we were at 0.63 brake horsepower, and when we dropped that down when we were at 900 CFM, when we dropped that down to a little below 50% at 410 CFM, we're at 0.13. So we've got some dramatic savings on our fan energy at that point. So now we look at the fan energy comparison over the course of the year for Dallas-Fort Worth, Texas. And we added in the single zone VAB, which is the shorter purple bars in each of the 12 months. Now it's pretty obvious here that the fan energy use in June and July is lower than in May or August, and it doesn't make sense. Except I ran this model as a classroom. So I assumed that that building was going to be unoccupied in June and July. So I dropped the occupancy, I think, to 0.1%. So we had a little bit outside air coming in, that kind of thing, but we were not going to use near as much energy and therefore not use as much fan energy as well. We didn't have any students in the classroom. I assumed a low occupancy just because there's going to be people working in the building for summer cleanup, that kind of thing. So that's why you're going to see some lower energy use at that point. If we look at our total energy comparison for Dallas-Fort Worth, you see that we have energy savings, again, every month using the VAV system. Unfortunately, this slide's not going to work because the way I had to present it, I've got part of it covered and it was supposed to uncover as I went. We're going to look at the total energy comparison for Dallas-Fort Worth. I can tell you that if we look at the constant volume with the forward curve fan as a baseline, your energy savings for cooling are going to be close to 50% annually for the building I model. Now that being said, generally speaking, the HVAC system in your building will be between 40 and 50% of your total energy use. The rest is going to be lighting and plug loads and that type thing, but your HVAC system is going to be about 40% total. So we can have a very significant impact on the utility bills for that building. The payback becomes fairly quick. Now I wanted to look at an ASHRAE zone map, and you can see the state of Texas is a lot in 3, quite a bit of 2, and then a little bit of 4 up there in the panhandle. So what happens with different climate zones? We looked at ASHRAE zone 3 already with DFW. So I decided to look at an ASHRAE zone 2, and we look at Houston, Texas. And we've got our fan energy and our total energy there. And what you see is the shape of that model is pretty much the same as it was in Dallas-Fort Worth. The magnitude will change. How much energy used in a given month will change because you've got a different weather pattern. However, the total energy used is still going to be pretty similar as far as percent difference. And I decided to look at one other one. I looked at a 2B, which is going to be El Paso, Texas. And again, very similar in shape, very similar in magnitude of savings, although the amount of energy used in any different month will be different. So to wrap this up, constant volume systems are unable to control relative humidity at part load. It's just not in their nature. When all you have is on and off, you don't have a good way of controlling your relative humidity. So if you've got a constant volume system, you must use your modulating hot gas reheat for humidity control, which is a very good method of humidity control, but not necessarily the best for energy for a lot of systems. You can improve the system efficiency some with an improved fan technology, but you're still limited because you've got a constant speed fan. By going to two-step compressors, you get better relative humidity control at part load compared to your constant volume system, and you get increased system efficiency. You're going to use less energy annually compared to that constant volume system. And then your single zone VAV system will have the best relative humidity control without going to modulating hot gas reheat, and have the highest overall system efficiency, meaning the lowest energy use for the same condition in that space throughout. at this time, we'll open up to questions that you may have on this.
Okay, we are going to open up for questions. Man, we just love technology. It's such a joy. We're all going to be so ready to go to Waco and all be together and not have to deal with this. But we're going to start. You guys already started putting in great questions. Keep putting those in. And Matt was letting everybody know in the chat that they do have the slides handy, and they can either send it to you guys after the session if you'd like to see it, or contact Matt, contact Eric through either.
Welcome to Click Meeting, your choice for audio and video conferencing. Please enter your
you can go ahead and reach out to Matt. You can reach out to Eric through the Texas Air System booth, and also through the networking section of this virtual
conference now. For help, please press *0.
Oh my goodness!
There are currently
so you can reach out to them and
other
they can
participants in the conference. The audio mode for this conference has been changed to listen only. You are now muted. To mute or unmute yourself, press *1.
I don't think he can hear.
I don't think I can, and I can't hear him. So, Eric, you're going to have to mute yourself. But we have a question from Richard. What part load and not, why part load and not VFR technology?
I think
he meant VRF.
Why are we not presenting VRF?
Yes.
Richard, I mean, VRF is a great technology, a great solution. That just wasn't what we dove into for the presentation. The presentation was for non-VRF DX systems, rooftop unit technology, just because there are so many districts that go with the small rooftop units, 1 unit per classroom type of a setup. So that was just the point of the presentation, was more for rooftop units. Mm-hmm. Hopefully that answers the question.
Yeah. Richard, if you want to, if you are interested in VRF technology, we will be having a virtual meeting on VRF applications in October. So stick around for that information. But today, we've got another question on what was, I'm sorry. Do you have any return on investment data between the 3 options?
Eric, are you able to hear? I think he's having some major technology issues. Yes, we do. I know that Aon's worked up several different ROI white paper options that we could send to you. If you want to come by and visit the booth, and we can connect that way and send you anything that you need.
I'm going to have Eric.
And that is something that slide shows, the one that didn't populate. And I could, well, I'll just send that to you directly. Essentially, if you start at where Eric started, which was the constant volume system, and work your way through, the single zone VAV ends up being something like a 50% energy reduction versus the first system that we looked at. So that's a quick, easy answer on the ROI, but if there's something more specific you want to look at, we can.
I missed Danny Helms because Danny always has to compliment people and be so wonderful that I just saw a great presentation and moved on. I'm so sorry, Danny. I missed your question. He says, can you discuss the pitfalls of slowing down your CFM fan too much?
Yeah, sure, Danny. There's certainly pitfalls both from a system perspective and from an equipment perspective, but the majority of those safeties are really built into the control, whether it's a manufacturer's control or a controls contractor taking control of the equipment. But certainly you've got the potential to freeze coils or those kind of things. But in a true single zone VAV system, that's not an issue, because you on the refrigerant side, you're modulating your both your refrigerant flow and your refrigerant temperature with head pressure control. But you also have freeze protection on the equipment. On the system side, you could eventually lower your fan flow so much that you could stall your fan. But with a good fan selection, you're probably not going to run into that. And then obviously that's taken into account with the setup and the control startup of the equipment. So those are a couple things that come to mind. But if you've got something more specific you want to discuss, let me know.
Eric, can you comment now? Can you hear us?
Yes, I can, if you can hear me.
We can.
All right, I finally got my auto figured out. One other thing that really needs to be looked at as you go into any VAV system is your diffuser selection. You need to make sure you've got adequate throw on your diffusers to get good mixing in the space where you're not just dumping that cold air out of the diffuser onto whoever happens to be below it. So it's got to be reviewed during design. As long as it's designed appropriately, it shouldn't be a problem as with any other VAV system.
This is not a wildly out there type system, excuse me, where the majority of good MEP engineers aren't going to understand those concepts.
Looks like Danny is typing again. Anybody else have any questions for Eric and for Matt? And remember, if you don't have to ask those now if you don't want to, or if you think about something later, you can reach out to both Eric and Matt through the virtual platform anytime. Danny asks, oil return?
Oil return can certainly be a concern depending on which compressor technology you use. Since what we're talking about here is packaged, it's nothing that really has to be dealt with in the field. That's going to be done through factory controls, either through some occasional flush cycles, that type of thing. But that will be monitored by the manufacturer and shouldn't be a field concern.
Okay. Any other questions for Eric and Matt? Well, like I was saying, if you do come up with some questions for Eric and Matt, you can reach out to them. The platform will be open through December 31st. And in fact, if you find yourself thinking about this presentation and going, you know what, I just need to see it again, you can. That's the beauty of this virtual platform. You can go back and watch this as many times as you want to, and you can reach out to Matt and Eric. You can find both of them at the Texas Air Systems booth. You can also find them through the networking feature, and those features will be open all the way through the end of December 31st. So watch this presentation again, reach out to them with your questions, your concerns. How would this work for you? And they would be happy to let you know how any and all of this could work for you and your organization.
Absolutely.
All right, guys. Any final thoughts, Eric, because you just kind of finally got to the party? Anything you would like to say to everybody else just to wrap it up?
Yeah. I would like to extend an invitation if you would like for me to come talk to you directly. I travel all the time. I'm happy to do that. I can coordinate that through Matt. And we'd be happy to come talk to you and help out with any of the concerns you have and any of your air quality issues. Let us try to help fix some of your problems. We'd be happy to do it.
Absolutely.
Great. Thank you so much, guys. We really appreciate your time. We thank you for all that, especially Texas Air Systems does for TEMA. We appreciate you so much, Matt. And Eric, thank you for coming and joining us today. We really appreciate you guys.
You bet. Thanks for having us.
Thank you for your time.
All right, guys, we're going to go ahead and end this session, and we'll see you at 10:30 for the next one. Bye.
Bye, everybody.